Hi everyone, my name is Sarah Crosby. I'm a PhD candidate and research assistant in the Mechanical Engineering Department at the University of British Columbia in Vancouver, Canada. And today I'll be talking about my research, which is a novel multi-domain hierarchical Bayesian model that we have developed to improve the prediction accuracy of occupant thermal satisfaction in open plan offices, and that takes into account measurements of CO2 concentrations as well as thermal IAQ metrics. So since the judgment of thermal comfort is a cognitive process, it is influenced by the occupant's well-being and overall satisfaction. And in recent years, there has been an increasing body of research examining the multi-perceptual and multi-domain nature of thermal comfort and IAQ. So we are looking at the thermal comfort more holistically by relating the occupant's thermal satisfaction not only to thermal conditions, but also to measurable non-thermal metrics of IAQ. So this study aims to fill a prevailing research gap with respect to standard models of thermal comfort, as they only take into account thermal factors when predicting thermal comfort, despite the increasing awareness of the interdependencies between perceived thermal comfort and overall IAQ. So this research aims to examine whether thermal comfort as perceived by occupants in a field data set can be attributable to one or several non-thermal parameters typically associated with indoor well-being. So we have developed a novel Bayesian approach that is capable of predicting the correlation between measured thermal and non-thermal IAQ conditions and perceived thermal satisfaction. So the thermal IAQ parameters that we have studied, represented by the F-set, are temperature, relative humidity, air velocity, and mean radiant temperature. And the non-thermal IAQ parameters that we have studied are noise level, indoor CO2 level, speech intelligibility index, and desktop illuminance level. And this is the Bayesian network diagram of our model framework. So for our first phase of this research, the field IAQ data that we have used are drawn from the cost-effective open plan environment, COPE, field study database that was made available for our research by the National Research Council of Canada. So the database consists of IAQ data collected from 779 workstations and 9 buildings across Canada and the United States. The IAQ data consists of physical measurements of thermal conditions, such as temperature, mean radiant temperature, and also non-thermal IAQ metrics, such as noise levels, light levels, and speech levels. So for every workstation, they have replaced the regular chair and put a cardstock chair system holding all the sensors. And in parallel with measuring the IAQ metrics, they asked each participant to fill out a survey, asking them about their right here, right now satisfaction with thermal conditions. So for the first phase of research, we have used the COPE database to develop our Bayesian regression model that uses Markov chain Monte Carlo inference methods to infer the posterior predictions of thermal satisfaction given thermal and non-thermal parameters of IAQ. So the posterior results revealed that the non-thermal IAQ parameter that showed a significant correlation with thermal satisfaction is indoor CO2 levels. So the results for the model containing CO2 concentration are showing an observable negative correlation between thermal satisfaction and CO2 levels, as you can see from the graph on the left. And model validation and checks revealed enough evidence to suggest that including CO2 in thermal comfort modeling improved its predictions. So for example, the odds ratio of posterior spaces is showing that predictions of occupants' thermal satisfaction is significantly influenced by CO2 concentrations. As you can see, 95% of the posterior distribution is deviated from 1. The posterior predictions of thermal satisfaction drawn from the model and generated from for different CO2 levels show that when the CO2 levels increases from 500 to 900 ppm, the thermal satisfaction decreases by 30%. So this current study aims to update the prior findings by adding 150 new samples of IAQ collected from a recent field IAQ study, test the significance and statistical robustness of the correlations between perceived thermal comfort and CO2 concentrations, and examine whether the prediction accuracy of thermal satisfaction can be improved upon adding measurement of CO2, and finally formulate a new hierarchical predictive model of thermal comfort that can be used by building modelers to improve the prediction accuracy of thermal comfort. So such observed results that have revealed the need for developing our own updated version of the data that aim to update and test the significance of the prior results. We have built our own high precision sensor card, and we have conducted a large IQ study on the University of British Columbia campus. The study consists of physical measurement of IQ and spatial and manual measurements, and also responses from an IQ questionnaire. The data were collected from 150 workstations in 5 different buildings between 2019 and 2020. And we have pretty much followed the same methodology in our previous study, so we can measure the incremental change in the significance of results upon adding the newly collected data. And in this work, the previous Bayesian framework that we have used in our first model is revisited, and we have developed a new hierarchical Bayesian framework that infers the occupant satisfaction as a function of indoor air temperature T and indoor air CO2 concentration C. So within the COPY and UBC dataset, there is a total of 14 unique subset field studies of individual buildings B. And here, T refers to the observed data from each individual test subject, of which we had 919 test subjects in total for the combined data set. The posterior predictions results of both data sets revealed a notable correlation between thermal satisfaction and CO2 level, which enforces the prior findings. And on the right-hand figure, this is a visualization of the posterior predictions of thermal satisfaction against both indoor air temperature and CO2 concentrations inferred from both data sets. So it presents a heat map of thermal satisfaction, where dark red represents maximum thermal dissatisfaction and green represents the highest thermal satisfaction predictions. So it is found from this figure that the negative correlation between CO2 levels and perceived thermal satisfaction is significant and reinforced. So now, after updating and verifying the prior study findings using the new data, indoor CO2 levels appear to be significantly correlated with occupant thermal comfort. And model checks have reinforced the previous findings that including measurement of CO2 is proved to increase the prediction accuracy of thermal satisfaction. So now we have formulated a new predictive model that is derived from the Bayesian logistic regression of both data sets. And the model evaluates the probability of thermal satisfaction as a function of indoor air temperature and CO2 concentration. So this is the posterior probability distribution of the proposed model's parameter beta, drawn from the MCMC sampling, with each beta's maximum posteriori map displayed within the 95% Kelvin interval. So it is shown that the CO2 model parameter credibly deviates from 0, and this observation suggests that the CO2 levels affect the logistic regression model in a statistically significant manner. So to conclude, this is the first known work to provide evidence that measured CO2 concentrations might improve thermal satisfaction predictions in a significant manner, at least in open plan offsets, and in a manner that can support future thermal comfort predictions. The new model can be integrated into building controls, predict occupant thermal comfort based on thermal conditions and ventilation rates, which might as well result in energy savings, while not sacrificing well-being and indoor air quality, which is an important challenge now after the pandemic. And as more IQ data is gathered in the future, our Bayesian model can be updated to provide more generalizable and universal results. Thank you.